Alright, welcome back to part 3 of our lecture about static stability. Now at the end of part 2, you learned that there were 3 fairly basic rules to figure out which of 3 categories of static stability you had in any given layer of the environment. You just found for that layer the environmental lapse rate and then compared it to the dry adiabatic lapse rate to determine whether the layer was statically stable, statically unstable, or statically neutral. And I promised you at that time that there actually is an easier way to do this, and more importantly, a more physically meaningful way, a way that we can kind of sort out and we can use these tools later. But that involves a new parameter to you, and that's called potential temperature. Potential temperature is a thermodynamic parameter. It's a state variable, to use the right term from like a thermodynamics class. It is a really powerful tool anytime you're trying to describe the thermodynamics of what's going on. Thermodynamics being that combination of temperature and pressure and density and so on. And so we have this variable called potential temperature, theta, and potential temperature is defined as the temperature our air parcel would be if we lowered the air parcel from the height it is now to the height where the pressure is 1,000 millibars. So you take the air parcel, let's just say it's at some height, some pressure P. Presumably that pressure P is lower than 1,000 millibars. In other words, the air parcel is higher above the ground than where you would find the pressure of 1,000 millibars. And then we lowered that air parcel to the height where it is a pressure of 1,000 millibars. And this gives you a temperature there. That would be the temperature the air parcel would be if you lowered it dry adiabatically to that level. Now, that actually is a pretty nifty trick. And there's a basic equation, theta equals, and then you see all that stuff on the right-hand side. You'll be doing that on a homework set and so on. But it's pretty slick, and you have to make sure that you use units of Kelvin for your temperature, both for the T in that equation and for the resulting value of theta. But actually this works pretty well. You just basically are lowering the air parcel. You are warming the air parcel at the dry adiabatic lapse rate as you move from one pressure to another. This is actually a variation on, you can derive this fairly simply from an equation you probably saw in like general physics that's called Poisson's equation. Poisson's equation was in general, like as you change the pressure of the air from one pressure to another, how does the temperature change? We're using a particular application of that. Instead of where Poisson was doing it like as they expanded the air from a, inside of a piston or something like that, how did the temperature change? Now we're doing it in the atmosphere as we go from one height to another. But this is a pretty nifty thing. Potential temperature is an astonishingly useful quantity. It is a great tool on the tool belt of anybody who is familiar with atmospheric sciences, because there's just 1,001 useful applications of potential temperature. And it has so many amazing properties. One of the most amazing properties of potential temperature is that it is conserved. That means that as we move the air parcel around, the potential temperature doesn't change. Conserved, I like this definition here, the one that I have marked with a star, to maintain a quantity such as energy or mass at a constant overall. So as we move the air parcel around, potential temperature is conserved. If we lift the air parcel, its temperature changes, its pressure changes, but its potential temperature, theta, won't. If we lower an air parcel, its temperature changes, its density changes, its pressure changes, but its potential temperature won't, because its potential temperature is an example of a conserved quantity. We'll see other examples over the course of the semester of properties of the atmosphere that are conserved versus other properties like temperature and pressure and so on that are not conserved properties. So in other words, if I take this air parcel and I lift it, as its height changes, its potential temperature won't. In other words, the change in potential temperature with respect to height, d theta dz, is 0. That is an amazing property. Here's another amazing property of the potential temperature. Since we compute the potential temperature based on the temperature and the pressure of the air, you can compute the potential temperature at the top of some layer of the atmosphere and at the bottom of the layer of the atmosphere. So you would get a change in potential temperature over the range of heights. You could figure out effectively an environmental lapse rate of the potential temperature. You can see how we could just do it there with the math, and it would be just like the potential temperature at the top minus potential temperature at the bottom divided by how far apart they are. This is something like a lapse rate, an environmental lapse rate of potential temperature, just based on observations along an instrumented mast or a weather balloon's flight or something like that. But it turns out that value, that partial theta, partial z, that is another way of measuring the static stability. So if we could compute the static stability of a layer of air, what we would find is we get three more rules. And these rules are in some ways simpler than the ones that we had that involved the environmental lapse rate. Because see, if we just have that the change in potential temperature with respect to height is less than zero, in other words, if the potential temperature is decreasing as you go up in the atmosphere, then our layer is statically unstable, and the layer is encouraging the motion of air parcels. On the other hand, if the change in potential temperature with respect to height is positive, in other words, as you go up in the atmosphere, potential temperature is increasing, then the layer is statically stable. In other words, that layer of the atmosphere is resisting the motion of air parcels and trying to return them back to their original altitudes. And in the case when the change in potential temperature with respect to height in that layer of the atmosphere is zero, then the layer is statically neutral and the layer is neither encouraging nor resisting the vertical motion of air parcels. See, that's kind of easier than the trick about environmental lapse rate and dry adiabatic lapse rate. Here you're just figuring out the sign of the environmental lapse rate of potential temperature, partial theta, partial z. Once you know its sign, just by like looking at a graph and seeing what the sign of is potential temperature increasing with height or decreasing with height, that's all you need to know the static stability. And that is a hugely useful tool. Like for example, here's a little graph that just shows a vertical profile of potential temperature on the x-axis versus height on the y-axis for like the lowest maybe 1 to 2 kilometers of the atmosphere or something like that. So I've got a boundary layer making up most of this graph, and then above that dashed line there we're up in the free atmosphere. And I just took this figure out of something from a completely different context. We're not going to get bogged down about why all the little dashed lines are on there and so on. But just looking at that graph of the potential temperature and height, we can see that we have three different regimes, if you will, here. Like in this case, down near the surface, we have a range of heights that I've marked in yellow there, where the potential temperature is decreasing with respect to height. The higher up I go, the less the potential temperature is. Well, when potential temperature is decreasing with respect to height, that means change in potential temperature with respect to height is negative. We know that means that this layer is absolutely statically unstable. Meanwhile, with this big fat layer, in the boundary layer there, where, gosh, the potential temperature doesn't really change very much at all with respect to height. In other words, partial theta, partial z, the change in potential temperature with respect to height in the layer, is basically zero. Well, we know that that means that that part of the layer is statically neutral. Air parcels that are being lifted or lowered in there, the layer is not either helping or encouraging that, nor resisting that flow. On the other hand, like at the top of the boundary layer and up into the free atmosphere, we see that the potential temperature is increasing with respect to height. Change in potential temperature with respect to height is positive, and therefore, based on the rules that we learned, that means that this layer is statically stable. Just knowing the sign was enough. There was no business if I had to compare this to the dry adiabatic lapse rate or anything like that. I can just look on a graph and say, oh look, potential temperature is getting lower as I go up, or potential temperature is constant with respect to height, or potential temperature is increasing with respect to height. Brilliant! Man, this is just one of my top 500 things to do with potential temperature, okay? This is a cool trick. And we wouldn't have had to just been a profile like that. Just to give you an example here I've made a cross-section of potential temperature across West Africa. My favorite place to do research type stuff. And so I just made myself a nifty little graph here of potential temperature with respect to height as we go from south to north, like the equator's on the left-hand side and the 40 north is on the right-hand side. And you can see how we're going across the Sahara Desert and stuff. The details here are not so important, but I just wanted to show you, well, as you go up on that graph, do you see how sometimes you are crossing lines of potential temperature? And I was going to tell you the name of them, but it's kind of a weird name. It's isentropes, but whatever. As you cross from like one color to another, you're moving from one potential temperature to another. If you look at the graph overall, you can see in general in this graph, the troposphere is such that potential temperature is increasing with respect to height, and that's true. In general, the troposphere is broadly statically stable. Okay? There are individual places, like down near the surface and so on, that might not be, but a good rule of thumb is by and large the atmosphere is statically stable. That's why we're able to get things like layers and stuff like that that persist. I mean, if the atmosphere was statically unstable, they would just drift away. They'd float away. We wouldn't be able to make layers to the atmosphere. That's kind of a philosophical point. But like, for example, most of the depth of the troposphere clearly has change in potential temperature with respect to height is positive. If I pick a location inside that circle there and go up, pretty much any place I go up, I'm encountering higher values of potential temperature than where I started. Change in potential temperature with respect to height is positive. That means that most of the depth of the troposphere in this case is statically stable. All right. Whereas I can pick another place, like this chunk of it that I have circled right there, where actually, you know, if I pick any location in there and go up from that location, I don't really cross a lot of potential temperature lines. I don't go from one color to another. By and large, in that layer, the change in potential temperature with respect to height is kind of pretty much zero. Okay? In other words, this is an example of a place that's statically neutral. If you actually compare that to that slice that I show you there in West Africa, you can see that that's actually over the Sahara Desert. Over the Sahara Desert, you're going to see that there's lots of mixing, and there's lots of, there's a reason why the potential temperature becomes constant with respect to height. In fact, why don't we dwell on that for just a moment here? I mean, now already twice, we've seen examples in which the potential temperature doesn't change with respect to height. In other words, the layer is statically neutral. In part 2 of the lecture, we saw that statically neutral also means that the environmental lapse rate was equal to the dry adiabatic lapse rate. What does this all have to do with each other? It's actually about this business that the potential temperature is constant with respect to height. Because potential temperature is a conserved quantity, and anytime you mix a property of the atmosphere that is a conserved quantity, it becomes constant with respect to height. Now that is a lot of jargon. Let me bring this simpler to you. Instead of talking about the atmosphere, let's talk about cake. Alright, over there on the top left-hand side of this picture here, we're making a cake, and we're ready to throw that bad boy in the oven, right? No, we're not at all. Clearly, we have not yet mixed the batter over there on the right. I see, on the left rather, I can see flour, and I can see eggs, and I don't know what else is all in there, but whatever. I see stuff. There's a certain amount of egg in that bowl. The total amount of egg in that bowl is a constant. It's a conserved quantity. When I mix the bowl, there's still the same amount of egg in there. When I mix the bowl, there's still the same amount of flour in there, and chocolate or whatever else is all in that picture there. But right now, inside the bowl, it's not very homogeneous. Inside of the bowl, it's very heterogeneous. If you had some kind of instrument that could measure how much egg is right here, and then you could use that same instrument and measure the amount of egg right there, it's not the same. D-egg D-Z, or D-egg dx, or whatever, you know, there's a gradient of egg here. And there's a gradient of flour. There's places with more flour, there's places with less flour. Okay? But these properties like egg and flour, they're conserved. Mixing the bowl does not destroy egg. It does not destroy flour. There's just as much flour before I mix it as after. But once I mix it, the distribution of the egg and the flour and so on becomes homogeneous. If I took my little instrument that somehow could measure egg, it would find the same amount of egg in every location inside the bowl, and the same amount of flour in every location of the bowl, and whatever else is in this cake or whatever they're making in these pictures here. In the same sort of way, when we have mixing in the atmosphere, any kind of process that is, any kind of property of the atmosphere that is conserved becomes well mixed. What kind of properties are conserved? Well, our first friend is going to be potential temperature. So if we have a layer of the atmosphere where originally potential temperature varied from one place to another, like maybe potential temperature was increasing with respect to height, or maybe originally potential temperature was decreasing with respect to height, that's over. As soon as we can have mixing, and we mix it all together, now we get with one kind of average potential temperature throughout the whole thing. We have mixed places that have higher potential temperature, places that have lower potential temperature, and we get the same temperature throughout. Now, you might think, but how the heck are we going to get mixing? And the short answer is, it's everywhere. Especially in the boundary layer. The boundary layer is a forest of invisible plumes of rising and sinking motion. As air parcels get slightly warmer and slightly cooler than the air around them, they'll rise if they're a little bit warmer, they'll sink if they're a little... I am so proud of this picture here, by the way, where I drew all these arrows on here, and they go behind the clouds and behind the whales. I'm so happy with how that turned out. Anyway, the boundary layer, though, near the surface is just rich with plumes of rising and sinking air. There's no shortage of mechanisms to be providing the mixing that would result in a situation in which potential temperature becomes constant with respect to height, which means the atmosphere is, down where this is all happening anyway, is statically neutral now, regardless of what it was before. If it was statically stable or statically unstable, once the mixing happens, it's statically neutral. That is so slick. I'm going to show you a couple more cool things you can do with all of this in the fourth part of the lecture. But before we get to that, let's do a couple quick questions. Question 7. Suppose that an air parcel has a temperature of 260 Kelvin and a pressure of 700 millibars. What is the potential temperature of this air parcel? Now, you could actually crank through the math, and I kind of encourage you to try. But in the meantime, let's just do it like thinking through what the signs would have to be and stuff like that. Would this mean that it is A, less than 260 Kelvin, B, more than 260 Kelvin, C, exactly 260 Kelvin, or D, this can't be determined from this information? What would be the potential temperature of that air parcel? Go ahead and figure that out and make a choice and get some feedback before you move on to question 8.